Swayam Prabha. Digital India. Educated India.
Hello everyone, and welcome to this concluding class of this course. And as you might be aware that in this class we will discuss the quantum dot devices. Specifically, we will discuss the IV characteristics of the devices, of these devices, and then we will have a short and I would say introductory discussion on the density functional theory, which is an ab initio way of calculating the electronic structure of nanosystems, and then we will briefly go through the entire course, or we will have an overview of the course summary. So let's quickly review what we have been discussing. So what we have seen so far is that in quantum dot devices, the device, the channel part, the active part of the device, that is modeled in this way by using molecular orbitals. And we have seen what happens when we put this quantum dot in contact with metallic bulk metal. So when the contacts are of bulk metal and we have a quantum dot in between, then in equilibrium, the change in the Fermi level happens because of the two processes. One is the quantum capacitance and second is because of the electrostatic effect. So when there is a change in the number of electrons on the quantum dot, just because of the change in the number, the Fermi level might change, and this is accounted for by the quantum capacitance. Similarly, when there is a change in the number of electrons on the system, that also changes the charge on the system, that changes the electrostatic potential energy of the system, and that is accounted for by the electrostatic capacitance of the device. And in total, we need to consider both of these effects, and so that's why the Fermi level of the device can be written as the Fermi level of the quantum dot without any connection, without the contacts, plus the contribution in the change of Fermi level due to quantum capacitance and the contribution due to the electrostatic capacitance. And pictorially, this is represented in this way, as you can see here. So the key point here is that the change in the vacuum energy is just because of the electrostatic capacitance, but the change in the Fermi level is because both the quantum capacitance and the electrostatic capacitance. So that's the key thing that we need to keep in mind while understanding the quantum dot devices. Then if we put a quantum dot and we put two contacts, bulk contacts on this quantum dot, this is the kind of device that we obtain, and these are the connections of the bulk contacts to the molecule or the quantum dots. And when there is no bias, in that case, the Fermi level across this entire device is uniform. The Fermi level of the source, the drain, and the molecule are at the same level. When we apply a voltage, as we also discussed in the last class, we need to understand two things here. One is, how is the voltage divided across the or how does the voltage drop across the device? In other words, where does the voltage drop in this device? And that depends on these two capacitors, the source and the drain capacitors, which essentially models the interface between the source and the molecule and the source and the drain and the molecule. So if both of these capacitors, both of these interface capacitors are same, in that case the voltage drops equally at both the interfaces in this way. And if one of the capacitances is large, let's say if the molecule is closer to the source contact as compared to the drain contact, in that case this voltage division factor, which we defined in the previous class, which is given as CD divided by CS plus CD, this tends to 0, and in that case almost the entire voltage drops across the molecule drain interface and not across the source and the molecule interface. So accordingly we can understand the electron transfer in these devices. The second thing that we need to understand is when there is an applied voltage, when a drain voltage is applied, it means that now the equilibrium is disturbed. So in this case there might be an electron transferred through this device, which will change the number of electrons in the molecule, which will change the potential energy of the system as well. So this change we need to understand, because the density of states depends on the potential energy of the system. Okay. So as we discussed in the previous class, the change in the potential energy is because of the two components. One is because of the charging energy, which is the electrostatic component, and second is because of the state filling, which is because of the change in the number of electrons on the system. So if at equilibrium, if the number of electrons on the molecule were n naught, which is governed by the equilibrium Fermi level of the system, EF, and the density of states of the system. So this is the equilibrium number of electrons on the quantum dot or on the molecule. But now this equilibrium is disturbed, and very soon steady state will be established. Steady state by definition is the state when the current through the device is constant. Okay. So in this case the number of electrons in steady state might be different than the equilibrium number of states. During this discussion I would recommend all of you to please have the discussion on the general model of transport in the back of your minds, because in that way you can draw parallels between the two, and this will also become easier to understand. So in steady state, if the number of electrons in the molecule is n, in equilibrium the number of electrons on the molecule or on the quantum dot is n naught. So there is this net change of n minus n naught on the quantum dot, and this change in the number of electrons will change the potential energy in two ways. One is the charging energy, second is the state filling energy. Charging energy is modeled by the electrostatic capacitance, and the state filling is modeled by the quantum capacitance. So that way this is the picture of the electronic energy levels, both before the charge transfer and after the charge transfer. So the net charge transfer is n minus n naught on the quantum dots. So this will bring a change in the potential energy, which is a sum of charging energy plus the energy because of the state filling. The charging energy is modeled by the electrostatic capacitance, and the state filling is modeled by the quantum capacitance. So this discussion we have had now multiple times. So finally the total I would say the total change in the potential energy can be written as a sum of these two components, and these two components are essentially written here. And this will there is a key point here, this U, the change in the potential energy of the system, depends on the number of electrons transferred, because it depends on delta n, and delta n is n minus n naught. So U is a function of n here. N is the steady state number of electrons on the quantum dot when a drain voltage is applied, when there is a bias across the quantum dot device. Please keep this in mind, that the potential energy of the quantum dot is a function of the steady state number of electrons on the quantum dot. Now with this we are in a position to sort of calculate the current across this system. So the system that we have is the source contact, the drain contact, and a molecule or quantum dot in a way. In order to properly understand the current flow in this device, when we apply a positive voltage on the drain contact, when a VDS is applied, let's break the current in the steady state in two components. One is known as the contact current, which is the current that flows into the molecule. The current from the contacts to the molecule is termed as the contact current, and the second component of the current is the molecule current, which is the current that flows out of the molecule. The total current will be a proper sum of these two components. Okay. So the reason that we are dividing the current in the system in two components, the contact current and the molecule current, is that the contact current depends on the occupancy of energy levels in the contacts. It depends on the number of electrons in the contacts, and the molecule current depends on the number of electrons in the molecules. Okay. So that's why we have divided these two the total current in these two components. So the contact current depends on the Fermi functions of the contacts. So the source contact current, which is the current that flows into the molecule from the source, is given by or will depend on the number of electrons going from the source to the molecule. So what the source tries to do is, the source tries to fill the quantum dot up to the source Fermi level, or in other words, the source tries to fill the states in the quantum dot according to the Fermi function of the source. Okay. So these are the number of electrons that the source can pump into the molecule or into the quantum dot. This is given by the density of states of the molecule times the Fermi function of the source. Please, if you recall the general model of transport, in that case also we had a similar term while calculating the rate of flow of electrons from the source into the molecule. There is a key point here. This density of state is the molecular density of state, and this is now shifted by the change in the potential in the molecule that is brought about by the change in the number of electrons. In our previous discussion, in the general model of transport, this GE did not had U in the argument. So the density of states here in this expression was just GE, but now we need to have GE minus U. Okay. So similarly at the drain contact, the drain would try to fill the quantum dot according to the Fermi distribution of the drain, or it will try to fill all the electronic states up to the drain Fermi level. So the number of electrons available at the drain for current conduction is given by this number. So if we define the transfer rate at the source and the drain contacts are as 1 by tau s and 1 by tau d. Tau s and tau d can also be termed as the transit times from the source contact and the drain contacts. So with this, the contact current, which is just because the current component because of the electrons in the contacts, is given by the source contact current is given as Q times Ns divided by tau s, and the drain contact current is given as minus Q times Nd divided by tau d. Generally, The reason for this negative sign is generally what happens is a positive voltage on the drain side allows electrons from the source to go into the molecule and from molecule to the drain. So that's why this negative sign is there. This we have taken a convention. If the electrons are going from the contact into the molecule, the current is defined as positive, and if the electrons are going from the molecule to the contact, it is defined as negative. So this is just the contact component of the current, which so the current is given as the charge transfer, which is Q times Ns divided by the rate time that it takes for the charge to travel through the device. Similarly, so this is the source contact current. Similarly, the drain contact current will be Q times Nd divided by tau d and minus because electrons are going from the molecule to the drain. So this is just the contact component of the current. Now let's come to the molecule current. So the molecule will have n number of electrons in the steady state, and what happens is if these electrons see any empty state in the contacts, then these electrons can hop from the molecule to the contact. The contacts, as all of us know by now, that the contacts are the continuum states. The contacts have continuum of states. So there might be some empty states as well because of the if we go by the Fermi distribution function at finite temperature, there might be empty states corresponding to the filled energy levels in the molecule. So there might be a component of current that is because of the electron transfer from the molecule to the contact. Okay. So this is given as, this is termed as the molecule current, and this depends on the number of electrons in the molecule, as similar to the, because the contact current depends on the number of electrons in the contacts, number of electrons available in the contacts for the conduction. Similarly, the number of electrons in steady state in the molecule is n, and if they find any empty state either in the source or in the drain side, they can hop into those states, and that will contribute in the molecular current. So the molecular current on the source side is the charge in the molecule divided by the time that it takes for this charge to go to the contacts. And in steady state, for positive drain voltage, generally the electron flow is from source to molecule to the drain. So that's why there is a negative sign here. Similarly, the molecule current in the drain contact is the charge available in the molecule divided by the time that it takes for this charge to transit to the drain side. Okay. So these are the molecular components. In the previous slide, we have the contact components. So finally, the net current in these systems is the sum of these two components. So the source component of the current is Q by tau s Ns minus n, and similarly the drain component is Q by tau d n minus nd, where n is the number of electrons in the quantum dot in steady state, and Ns and Nd are the number of electrons in the source and the drain contacts. And if we in steady state, these two, there is a constant current throughout the device, so this Is should be equal to Id, and if we equate these two expressions and if we replace it back to these expressions as well, then we obtain the expressions for the steady state electrons in the quantum dot and the steady state current in the system. By equating these two equations, by putting them equal to each other, because in steady state Is is equal to Id, we will obtain the expression for n. And if we replace this n into this equation or this equation, we will obtain an expression for I. So I would recommend all of you to do this derivation. So I am skipping this step, and as I said, this is quite similar to to the calculation that we did in the general model of transport. It actually draws parallels from there. NS and ND are given by the expressions in the previous slides, these expressions essentially. Okay, depends on the source Fermi distribution and the drain Fermi distribution function. So with this, we have the expressions for the steady state electronic number and the steady state current in the device. Okay, so this is the IV characteristics, or this gives the IV characteristics of the quantum dot device or any nanostructure in a way. Okay, but if you have a careful look at these equations, there is a catch in these equations, and the catch is that n, which is the number of electrons, it depends on u, because the density of states depends on u, and u in turn depends on n, because if you go back and just to quickly review, the change in potential u is a function of n. It depends on n. It in fact u depends on delta n, which is n minus n naught. N naught is the equilibrium number of electrons. So that is the catch in these equations, that the steady state number of electrons depend on u, which is in turn function of n. So this is not a closed form solution, or this is not a closed form equation, I would say. We cannot have a closed form solution of these equations. And that's why what we do is, with these equations, we need to do the what is known as the, we need to, in order to solve these equations, we need to use the iterative method, or what is known as the self-consistent solution, self-consistent approach to solve these equations. So the way this works is that we make an initial guess of u, and with this guess we calculate the density of states and calculate the steady state number of electrons in the system. From this value, from this n, we can calculate n minus n naught, which is delta n, and from delta n we further calculate u, which is this, and this will also have the quantum capacitance component. Okay. Then with this u, this new u that we obtain in this step, we compare this with our initial guess, and if both of them match with fair accuracy, they are fairly close to each other, or they converge to a particular value, then we take that to be the final u, and based on that u we calculate the steady state current in the system. But if this and the initial guess do not match, then we again go back to this step. We again with this u we calculate n, from this n we calculate a new u, we compare this one and the previous one. If they converge, then we calculate the steady state current, otherwise we go back. So this is the iterative way to calculate the solution of these equations, because we cannot have the closed form solution, and this is known as the self-consistent approach to solve these equations. And this essentially completes our calculation of IV characteristics of the quantum dot devices. Okay. So I would again recommend you to go back and derive these two equations from the contact current and the molecule current, and then this iterative or the self-consistent approach will give us the final solution of the steady state current and the steady state number of electrons in the system. Okay, so that's essentially what we have on the quantum dot devices, 2-terminal quantum dot devices, and this discussion can also be extended to the 3-terminal devices, the way we extended the general model of transport discussion to MOSFETs as well. Okay. So, with this, now we come to our last topic of this course, which is the density functional theory. So, it has prominently, it has two terms, one is the density, second is the functional. So, this is the theory, or this is a method to understand the quantum mechanical behavior of many body systems, multi-electron systems, nanosystems actually. And this is an ab initio approach, ab initio method to calculate the electronic structure of atoms, molecules, crystals, surface and their interaction. So, it is heavily used in computational chemistry, it is used in condensed matter physics, it is used in electronics, it is used in material science nowadays. So, this is one of the, I would say, most important quantum mechanical method to understand the electronic structure, electronic properties, and also nowadays magnetic properties of the atoms from first principles. Because in our discussion of in our previous discussion, what we have assumed is that we know what is the band structure of the device, what is the band structure of the channel, and from that we can calculate the density of states. From that we can from there we can calculate the modes, we can calculate the current, we can calculate almost all the electronic properties, electronic characteristics of the device. But if we have a novel structure, if we have a new kind of structure where we do not know anything, we don't know about its EK relationship, we do not know about its band structure, we need to start from the first principles, and that's why it is known as the ab initio method. It makes some approximations, because without approximations we cannot solve the quantum mechanical equations, and very soon it will be clear why this is known as the density functional theory. Okay. So, let us begin with the basics of this. If we have any quantum system, all the information about that system is encapsulated in the wave function of that system, and the wave function is obtained from the Schrodinger equation. The Schrodinger equation is a very simple, I would say, simple and elegant equation. It relates the Hamiltonian, which is the total energy operator of the system, and if we operate this Hamiltonian on the wave function of the system, it gives us the energy corresponding to that wave function. So, by solving this equation, we can obtain the energy states, various energy states and various eigenstates and eigenvalues, energy states as well as the wave functions corresponding to those states. Okay. So, this is where we need to start from if we try to understand any new system, any unknown system. This is the starting point. But for multi-electron systems, for example, in a quantum dot system where we have few hundreds of atoms, in which we have, let us say, few hundreds of electrons interacting with each other, only external electrons are interacting, let us say, outer orbital electrons are interacting, let us say. So, in multi-electron systems, the Schrodinger equation transforms into this way. This Hamiltonian now has three components, prominently three components. One is the kinetic energy of the electrons, which is given by the kinetic energy operator. Let us say there are n number of electrons in the system, capital N number of electrons. So, the Hamiltonian, which is the total energy operator, is essentially the sum of the total energy of the electrons will be the sum of kinetic energy plus the interaction energy of that arises because of the interaction of electrons with the nuclei in the system, or atomic cores in the system, positively charged atomic cores in the system, that is given by this second term. And third is this electron-electron interaction, which is given by this third term. So this is the scenario in multi-electron system. There is in total energy, there is this nuclear kinetic energy term as well, but since it is assumed that the nuclei, various nuclei in a system are almost fixed, because the mass of the nucleus is extremely large as compared to the mass of electrons, so their velocities or they do not basically move, so their kinetic energy is assumed to be negligible. And if we are only interested in the electronic structure, these are the three components of electronic energy that we need to consider. One is the kinetic energy of electrons given by the kinetic energy operator. Second is the electronic interaction with nuclei given by this electrostatic potential V. Third is the electron-electron interaction given by the electrostatic potential energy U. And if we, in this n electron system, if we try to find out all the properties of this system, or we are trying to understand this system, we need to finally calculate the wave function of this system. And we need to put this Hamiltonian in Schrodinger equation, and this is finally what we obtain. This is the equation that we need to solve for an electron system. For a multi-electron system, the wave function looks like this, which is essentially the product of the wave functions of different electrons. And if you have a careful look, each of these wave functions, so this psi 1, psi 2, psi n are the wave functions of first electron, second electron and nth electron. And if we have a careful look, each of these wave functions is this psi, each of these psi is a function of three variables, three space variables. If we are just considering the space dimension, we are not considering the time evolution at the moment. And this n electron wave function is a function of 3n variables now, and that's a problem actually. So in multi-electron systems, this Schrodinger equation involves a wave function that is a function of 3n variables, and if n is few hundred electrons, only few hundred electrons, small systems, even in that case, this equation becomes almost impossible, or impossible to solve actually. This becomes unsolvable. And that's the, in other words, what we can say, that's the curse of the dimensionality. Because as the number of electrons increase in a system, the dimensionality, the dimension of the wave function increases, which increases the dimension, and the correspondingly the dimension of all the operators Hamiltonian will increase. The calculation will become just impossible. So we cannot directly solve the Schrodinger equation for this system. One reason is this, second is this. This interaction is also extremely difficult, this interaction term. So instead of dealing with the wave function, what we deal with is the density of electrons, which is defined as in this way. I is from 1 to n, psi I star psi I, summation of all the electrons. So if you remember, psi star psi is known as the probability density. So this gives us, this is known as the probability density function, and if we integrate this over space, this gives us the probability that an electron will be found in a certain region of the space. On the similar lines, this electron density function is defined for all the electrons. So what we assume is, we assume as if there is an electron distribution in the system, and electrons are distributed in a certain way, and this is defined by n, or sometimes rho as well. And now this probability, or this electron density function, is just a function of 3 space variables. It's just a function of 3 variables. Whatever be the number of electrons, whatever be n, capital N, if you just to quickly remind, the wave function is a function of 3n variables, but the electron density is a function of just 3 variables, 3 space variables, if we are just considering the time independent part. If we can somehow sort of reformulate this Schrodinger equation in terms of this electron density function, then we would not need to deal with 3n variables in the wave function and large matrices, and in that way we can somehow manage this calculation. And that's essentially that lies at the heart of the density functional theory. That's where this first term density comes in this DFT, because instead of directly dealing with the wave function of electrons, it deals with the electron density function. Whatever be the number of electrons, the electron density function will just be a function of 3 variables. So this curse of dimensionality has been, will be, or is dealt with by dealing with the electron density function instead of dealing with the electronic wave function. But how do we deal with this electron density function? How do we solve, or in a way solve, this Schrodinger equation using electron density wave function? And I would say this, the credit goes to the 2 theorems given by Hohenberg and Kohn in early 1960s. So what these theorems do, they sort of reformulate our problem of solving multidimensional Schrodinger equation in solving or finding out the electron density. So let's go through the theorems first, and then it will become clear. So what the first HK theorem, Hohenberg-Kohn theorem, says is that the total energy of the system is a unique functional of the electron density. So what it means is, if we go back to the previous slide, the electronic energy, the energy of the system, depends on the Hamiltonian. According to the Schrodinger equation, it depends on the Hamiltonian, and we need to solve the Schrodinger equation. But what HK theorem says is that this energy of the system is a unique functional of the electron density. So we can somehow calculate the energy from the electron density. It depends on just on the, it's a unique function. And now this functional is a new term here. Functional essentially means functional is a function actually. So it is a function whose argument is also another function. Okay, so in a way, very loosely defining very loosely, it is a function of functions. More rigorously, it's a function which maps from a space of functions to a field of scalar, a field of real or complex numbers. So it's a map from the space of functions to the field of real or complex numbers. In simple words, the argument of a functional is a function, and it gives us a real or complex number. That's known as the functional. So what this first HK theorem says is that the total energy is a unique functional of the electron density. And that's where this second term in this DFT comes from. So it deals with electron density and it deals with the energy functional, because energy is a functional of the density, which means the energy of the electrons is a function of electron density function. Okay. So the first theorem sort of conveyed that the energy can be calculated from the electron density function, and this is sort of the form of this energy functional. The energy functional can be written as sum of two components. One is because of the external potential. External means interaction of electrons with nuclei, with atomic cores, plus in a way intrinsic energy functional. We'll come back to this. This is because of the electron-electron interaction in the system primarily, plus the kinetic energy, but kinetic energy is not dependent on the electron density, so it depends on the electron-electron interaction. The second theorem says, what the second theorem says is, second HK theorem, that the ground state energy can be obtained variationally. Variationally means by minimizing it as a function of the electron density. So the electron density that minimizes the total energy is the ground state, exactly the ground state density of the system. So what it says is that we need to find out the electron density function Nr, and we need to find out that electron density which minimizes the total energy function, and that will be the ground state electron density function. And as a consequence, or one of the consequences of these HK theorems is that, or one of the, I would say, side results is that from a ground state density function, from the ground state density of electrons, in principle it is possible to calculate the corresponding ground state wave function. So the HK theorems, essentially what HK theorems do is they reduce the Schrodinger equation, the original Schrodinger equation, to finding out the density, electron density of the system, and by minimizing the energy as a function of the electron density, we can find out the ground state energy. And the ground state is important because that is the state when the system is not interacting with any external agency. That is the state that gives us the electronic structure, the band structure of the system. But they do not tell us about how to calculate the electron density. They say these HK theorems tell us that the total energy of the system is a functional of electron density, and the electron density that minimizes this energy functional, that corresponds to the ground state density. And from the ground state density we can calculate the corresponding ground state wave functions, and from there we can calculate all the electronic properties, we can calculate all other properties of the system. So these theorems are at the heart of the density functional theory, and that's why this theory is known as the density functional theory, because it deals with the electron density function, and it deals in this method the energy is a functional of the electron density. That's why density functional theory. Okay. There are before going into there is one question that stands here. That is, how do we calculate the electron density? How do we calculate this Nr at the first place? Before going into that, let's have some. Let's try to understand this multi-electron Hamiltonian. Let's try to understand the important parts of the Hamiltonian. So the first part of the Hamiltonian is the Coulomb potential part, which is the Coulomb potential, everybody knows, is the classical potential due to a charged particle, and it is generally used to account for the electron nuclei interactions. So it accounts for the interaction of electrons with the atomic cores. Second consideration or second important idea is the idea of Hartree potential. So that lies at the heart of calculating the electron density function. So what Hartree potential is that we reduce this problem of interacting particles, multi-electron particles, into a problem of non-interacting particles. So what we do is that this electron-electron interaction is effectively reduced or is modeled as an effective potential known as the Hartree potential, and by considering the Hartree potential we can assume that each electron is moving independently of each other, just feeling the average electrostatic field which is given by the Hartree potential. So this Hartree potential in a way sort of encapsulates the electron-electron interaction, and it gives us an electrostatic potential or the effective electrostatic potential in which we can assume that the electrons are moving independently of each other. So this electron-electron interaction has been modeled by this Hartree potential. But there is more to it. There is this exchange interaction as well, and this exchange interaction comes from the spin properties of the electrons. And in order to understand that, we need to understand we need to go back to the Pauli's exclusion principle, which says that the two identical spin electrons cannot occupy the same quantum state. That in other words, what it means is that two electrons of the same spin cannot be at the same place at the same time. Two electrons of opposite spin can occupy the same orbital, but the two electrons of the same spin cannot occupy the same orbital, same state. Okay. So the exchange interaction is essentially it due to this principle, due to the Pauli's exclusion principle, two electrons with parallel spins, with identically oriented spins, are not allowed to sit at the same place. This in a way gives rise to an effective repulsion between the electrons of parallel spins. It is not an electrostatic repulsion in a way, because electrostatic repulsion is modeled by the Hartree potential. It is entirely a quantum mechanical kind of interaction that arises because of the Pauli's exclusion principle, where two electrons with identical spins cannot be at the same place. So effectively it can be termed as, or it can be termed as an effective repulsion, and also known as the exchange interaction. Repulsion between identical spins electrons. So please remember that it is different from the Coulomb-Coulomb interaction. It is different from this electrostatic interaction. Its origin is in the spins or Pauli's exclusion principle. Similar way, there is this correlation interaction, because according to the Pauli's exclusion principle, two electrons of opposite spin can be at the same place, but two electrons, when they try to come to the same place, there will be a electrostatic repulsion. So they cannot exactly be at the same place, but there is a sort of correlation between the opposite spins. That is purely of quantum mechanical origin, and that is modeled by the correlation interaction. So apart from the Coulomb interaction, so this Coulomb interaction is, Coulomb potential is the interaction between electrons and nuclei. Hartree potential accounts for the electron-electron electrostatic interactions. And then this exchange and correlation interactions are, they arise from the quantum mechanical properties, they arise from the spin properties of the electrons and governed by the Pauli's exclusion principle. Effectively, they can be written as repulsion forces or correlation forces in a way, coupled forces. There is a coupling between there is a coupling between opposite spins and repulsion between the parallel spins. So finally, the effective potential in a multi-electron system can be written as a sum of electron nuclear interactions, Hartree potential, and exchange correlation term. X means exchange, C means correlation, so it accounts for both exchange and correlation. And with this, we can now say, or we can now treat the electrons independently. This interacting electron system can now be treated independently by considering Hartree potential, this electron nuclear Coulomb potential, and the exchange correlation potential. With this, now we come back to the HK theorems, and the thing here was that we do not know how to calculate the electron density function, and that problem was solved by Kohn and Sham in 1965 by what is known as the Kohn-Sham equations. And Kohn-Sham equations are the equations for non-interacting electrons in a way. So the interacting electrons, by using the Hartree potential, have been or can be considered to be non-interacting, and we can write down the Schrodinger equation for these this fictitious system, for this non-interacting system, which is an approximation of the interacting system. But now this potential is modified by the Kohn-Sham potential, which is essentially the sum of external potential, which is electron nuclear interaction, Hartree potential, which is the effective potential arising out of electron-electron interaction, plus this Kohn-Sham, plus this exchange correlation term. So in this method, what we do is we solve the equations or these single particle Schrodinger equations, also known as Kohn-Sham equations, and we calculate the solution of these equations known as the orbitals, phi orbitals. And if we consider this Kohn-Sham potential properly, then the electron density can be calculated from these, the solution of Kohn-Sham equations from the orbitals phi's in this way. The key point here is that this Kohn-Sham potential needs to be properly accounted for, and this effective potential that we discussed is essentially the Kohn-Sham potential. So this is what we need to properly find out, and it has three components. The first one is the electron nuclear interaction, which is relatively easy to calculate. We can calculate this, but this second potential, the Hartree potential, which is the effective electrostatic potential arising out of electron-electron interaction, this depends on the electron density. So it's also a functional of electron density. Also, the exchange correlation potential is a functional of electron density. The difficult one, this Hartree potential functional, is calculated from the Poisson's equation. Exchange correlation is a more difficult one, and there are multiple approximations to calculate this exchange correlation component. The two most popular ones are the local density approximation, LDA, or generalized gradient approximations. So I'm not going into the details of these approximations in this class, but from these we can calculate this exchange correlation component in the Kohn-Sham potential functional. This Hartree potential functional can also be calculated from the Poisson equation, and that way we have this Kohn-Sham potential functional. And once we have this, by solving this single particle Schrodinger equation, Kohn-Sham equation, so-called Kohn-Sham equation, we can calculate the orbitals, these wave functions, and from this we can calculate the electron density. But again, there is a catch here, because the density depends on these wave functions phi's, and the phi's depend on the solution of this equation, but this equation in this equation this potential functional depends again on nr. Okay. So, this is not a closed form, again we cannot have a closed form solution for this system of equations, and that is why we again need to use the self consistent approach. So, what we do is we make an initial guess of the electron density. From this electron density we calculate the Kohn-Sham potential functional. From this we calculate these orbitals, phi orbitals. From these orbitals we again calculate the electron density function, and we compare this initial guess. This is the first we make the guess, we compare n naught r with nr, and if both of them converge then we calculate the final density from this equation. This is the final density, the conversion value, and from there we can calculate the ground state energy as well according to the HK theorem, second HK theorem. If they do not converge, we again go back, and with this new density function we again calculate the Kohn-Sham potential functional. From there we again calculate the phi values, phi orbitals. From there we calculate the electron density function, and this process goes on. This is known as the self consistent approach to solve the Kohn-Sham equations, from which we can calculate the electron density function. So, this in summary is the density functional theory. There are and this is a very quick review or very quick introduction to the DFT, and if you are interested, this is, I would say this is one of the most important calculation method in multiple disciplines nowadays. So, I would recommend all of you to go back into studying the more details of this method. So, with this we finish this course, and as a just to have a quick relook at this course, we will see what we have seen so far. So, we started with the background, why we want to study this kind of course, because, and that goes back to the scaling of devices, because by scaling nowadays the devices are becoming extremely small, few tens of nanometers, and even some devices are nanostructures nowadays. So, we and because of this scaling, the conventional theory of transport is not sufficient to explain and understand the electronic properties of these devices. They cannot explain the voltage drop in the devices, energy dissipation, IV characteristics, all the things essentially. So, we need to take entirely different approach, and so that is why we start with the basics of quantum mechanics, because in order to understand anything we need to go to the basics. And so, in the initial classes we went through the basics of quantum mechanics, through the postulates of quantum mechanics, then we solved the free electron wave functions, then the wave function for an electron in a potential wave. What we see from here is that the confinement of electrons lead to discretization. That is a direct consequence of the quantum mechanics. Then we delved into the idea of density of states in the devices, especially of the channel, and that we can obtain from the EK relationship. Between them we also dealt with the chronic Penny model, or how the electrons behave in solids essentially. So, after the density of states we try to understand the Fermi level, the idea of Fermi level, Fermi distribution function, because in a device generally the channel region is extremely small. So, we need to understand the density of states of the channel. The contacts are bulk, we need to understand the Fermi distribution functions, the Fermi levels of the contacts. That is what we did, and what we went through is that the Fermi level in equilibrium is invariant across the entire device, entire system. Then we studied the general model of transport, which is actually a generalization of Landauer's model of transport, where the contacts are modeled by the Fermi functions of the contacts and the Fermi levels, and the channel is modeled by the density of states. in the general model of transport, we could, from this general model of transport, we could find out the IV characteristics or the current and the steady state number of electrons. We could also, or we came across many new properties as well. For example, the number of modes in a device, the broadening of energy levels, which is due to the finite lifetime of electrons in a system. The notion of the transmission coefficient in a diffusive transport case. This also we came across in the general model of transport. Then we studied this idea of modes in great details in all 1D, 2D, 3D devices and compared it to the idea of density of states in 1D, 2D and 3D systems. Then we tried to understand the notion of voltage drop and energy dissipation in ballistic transport, and we calculated various device parameters for a two-terminal device from the general model of transport. The important one is this calculation of conductance in near equilibrium transport case, and we did this calculation for multiple different temperatures, different materials. Then we had a discussion on the subbands in 1D and 2D materials, because in practice 1D and 2D materials are not actual 1D, 2D materials, they are quasi 1D and quasi 2D materials. So electrons can move in one direction freely but confined in other two directions in 1D materials. Similarly, in 2D materials, electrons can move in two directions confined in the third one. And that's why in this confined direction, energy states become discrete, and we need to consider the subbands because of these discrete energy levels. So that's what we discussed. Then we went to understand the three terminal devices, essentially the MOSFET device, which is the main component of electronic devices in today's world. We try to understand the IV characteristics of the MOSFET. We had a discussion on the conventional MOSFET theory in the beginning. Then we went to the MOSFET transport theory. We applied the general model of transport on the three terminal device on the MOSFETs. What we could see is this was one of the most important discussions in the MOSFET transport, that MOSFET is a barrier control device. So there is a barrier from the source to the drain in the MOSFET, and the velocity at the top of barrier is very important, and we try to understand the saturation of velocity in ballistic MOSFET. So in general MOSFETs, the velocity saturates because of the collisions, but in ballistic MOSFETs, it is not due to collision, it is because of it comes from the electronic structure distribution of velocities in MOSFET at the top of the barrier. So that's what we discussed. Then we went to understand the MOSFET electrostatics. First, the conventional MOSFET electrostatics. We had a detailed discussion on the charge in the semiconductor as a function of the semiconductor potential, relationship between the semiconductor potential at the interface to the gate voltage, the relationship between the mobile charge and the gate voltage. We could also understand the notion of the threshold voltage, which is the gate voltage at which the inversion happens. We also delved into the idea of gate capacitance, which is essentially has two components in series. One is the oxide capacitance and second is the semiconductor capacitance. We discussed this both at low frequency and high frequency. Then we discussed this important consideration in MOSFET electrostatics, which is the 2D electrostatics, which is prominent in modern day nanoscale devices. And what we saw was that because of this 2D electrostatic effects, the threshold voltage is reduced or the gate control is reduced on the channel. And as a method of countering these 2D electrostatic effects, we discussed the idea of geometric screening, which is done by surrounding the channel with the gate on multiple sides. Okay, so after the 2D electrostatics, we had a discussion on the strain engineering, how the strain can enhance the performance. Strain applied in certain directions can enhance the performance, the better current in a nanotransistor. Then we discussed the thermoelectric effects, prominently two effects. One is the Seebeck effect and second is the Peltier effect. We discussed the notion of charge current and heat current. Seebeck effect essentially relates to the development of, or because of the temperature difference, voltage is developed across a semiconductor. The reverse happens in the case of Peltier effect. Because of a current flow in a semiconductor, the heat current also flows, which develops a temperature difference. So that's what we discussed in thermoelectric effects and derived the Seebeck coefficient and Peltier coefficient. And in last few classes, we have been discussing the quantum dot devices, and we have a very short and quick introduction on the density function theory. So that's essentially what what was the subject matter of this course. I hope all of you enjoyed this course. If you have any feedback about the course, please give it to me either on my email ID or on the course page. And finally, I would again thank you for enrolling for this course. Thank you.